Good afternoon. Today is our lecture number 17. And welcome back from spring break. And I know that you worked through spring break on the project and other things. So the project is due in a couple days, which means that today will be our last class to ask questions about it. I'll be here tomorrow as well during my office hours, and but I won't be here on Thursday. Now, to submit the project, you can either, remember you have to print according to what I said there, except the output files, we just talked about it. Print everything, the handout, sign it, put in your formulations, derivations, input files, the plots, and so on. Staple everything, and put it under my door before midnight. If you cannot get to the suite, you can scan it and send it to me, and then you can turn in the hard copy the next day on Friday, or I'll be here on Friday, or Monday, or Tuesday next week, okay? Basically, the assignment consists on slightly modifying the code that we developed in class, the Fortran code. You could also do with the MathCAD code, but it's a lot more work. I told some of you who were opting for that option of using the MathCAD code. You'll have to just hardwire it from scratch, especially building the geometry would be a lot more difficult. Because in the Fortran code, we develop a preprocessor, which you basically give the segments and the discretization, it will do the geometry for you. So building the input file is just basically coming up with the configuration of the segments, the discretization, imposing boundary conditions, and then you had to modify things on the code to make those boundary conditions work, because I purposely left out third-kind boundary conditions on the code. So you have to do the algebra of how to modify, of how to switch the rows of the matrix when the boundary condition is type 3. So I trust by this point everybody's got that working, and you're just basically working on the report. What I'm going to do today, and what we actually did the last two lectures, is talked about the dual reciprocity method as a way of handling the situation of having a generation term on the equation, which we don't have on that other code. All right. So what I'll do today is show you some modifications of the code that I made to be able to handle that, to be able to implement the dual reciprocity method, which might be useful if you haven't finished your project, because you can see how I do things. I didn't implement third-kind boundary conditions, but I modified some other things in the code to make it work. And this is basically going to be our last lecture on boundary element method. Obviously, boundary element method is much more extensive than just what we cover in this class. We covered about 4 weeks of it. We can do 2 semesters of boundary element method. It doesn't stop here. There's boundary element methods for structure, so handling the Navier equation, and that's actually how it originated. Not for heat transfer, but for structures, for the equations of elastostatics, or Navier stresses and strains. And the fundamental solutions, the green functions, are completely different, and the implementation is completely different because it's a vector equation rather than a scalar equation. There are ways of handling, for example, transient problems. Okay, we have talked only about steady problems. Okay? Steady heat conduction with generation, that's it. So there's ways to handle transient problems in many different ways. We can use dual reciprocity to handle transient problems. We can use what they call convolution fundamental solutions. This is a much more involved process, but it's more accurate. It's also more computationally intensive and memory intensive, so I always discourage the use of that. I've tried it and it works, but it's just for toy problems. If you want to do a real problem, you cannot use it, because it's a massive amount of resources that you require to be able to implement it. So basically, what I wanted to give you is an exposure to the boundary element method. Tell you that it's out there and that it's good for these type of problems, for potential problems, for problems that have some sort of generation that can be handled by these dual reciprocity method, because we can actually keep everything on the boundary. The whole point of it is, can you keep everything on the boundary? Once you start getting into problems that are of a completely different nature, like fluids, for example, where there's convection effects inside the fluid flow. Now, naturally, you would think that inherently that problem cannot be handled from the boundary. You have to do something to the interior to be able to capture that behavior. And that's a problem. People try in the boundary element community, which is a sizable research community, there are people trying to handle problems using boundary elements and doing a lot of maneuvering of the method to be able to capture and handle many different types of problems that by nature cannot be handled by the boundary element method because it cannot physically be represented through the boundary. Okay, so boundary element method is a great method for what it can work, for what it can actually do. All right, when you're talking about potential problems, when you're talking about acoustics, when you're talking actually fracture mechanics is one example of when the boundary element method is the only method that works. Because fracture mechanics or cracks, the tip of a crack is a singularity. And of all the methods, the boundary element method is the only one that's based on a singular fundamental solution. So when you're talking about handling fracture mechanics, cracks, and crack propagation, boundary element method is the way to go. So we're gonna stop at this, at potential problems and potential problems with generation. We're gonna implement it today, so you see some examples, and that will give us a natural progression to our next part of the semester, which starts next week, which is meshless methods. Because with meshless methods, we can do whatever we want. We don't have to stop to look at the nature of the equation, whether the equation is linear, non-linear, it has generation or not. Whatever equation we're given, we can handle, okay? It obviously has drawbacks, but at least it's a method that is very easy to implement. And the reason why this provides a good transition is because the meshless treatment that I'm going to present to you is going to be based on these radial basis functions that we're using in dual reciprocity, okay? So it's a natural transition. So, sorry. Implementation of the dual reciprocity boundary element method in Fortran. And again, I'm going to use Intel Visual Fortran as the medium. Okay, it's basically writing on plain Fortran 77. And again, remember that the equation that we're trying to handle is, recall, if we're given the Laplace of the temperature is equal to minus b of x, such that b of x is some generation UG triple prime, which can be a function of position divided by the conductivity. Then the dual reciprocity or the discretized boundary integral equation becomes and this Hij, or the influence coefficient matrix, same thing as for the standard boundary element method. And the Gij is the influence coefficient matrix G, standard for. And the only difference between these particular discretized boundary integral equation and the other one is that we have this extra term B here, such that B is the integral over the domain of this function Bx times the fundamental solution x collocated at points I, which through the dual reciprocity boundary element method results in second true dual reciprocity boundary element method, this results in the summation from k equal 1 n plus ni of alpha k times the summation from j equal 1 to n of pj k gij minus the summation from j equal 1 to n of uj k hij minus c of psi I times u k of psi I. Right? And I can tell you what that u, that p, and that alpha are. Such that the coefficients alpha k are obtained from expanding d of x as, so we let d of x be equal to the summation from k equal 1 to n plus ni of alpha k, some expansion functions f of k. All right, we covered all this in the last 2 lectures. I'm just summarizing everything in a page and a half so that we can identify things on our code today. Therefore, collocating the above at x equals x1, x2, all the way to xn plus ni, we end up with a system B is equal to f times alpha, where then alpha can be calculated as f to the minus 1 times b. Recall also, so in this expression here of b, we have the p and the u. Recall that u k of x is such that f k, which are the selected expansion functions, is equal to the Laplace of u k of x, and hence the expression dual reciprocity, because we decide arbitrarily to expand b in terms of some arbitrary expansion functions, and then we require those expansion functions to be the Laplace of something else, and then we apply the Green's identity and so on. And p k of x is equal to the normal derivative of u k of x. All right. Now for the current implementation, I've selected the polyharmonic splines for the expansion functions. For the current implementation, use the standard polyharmonic RPF, radial basis functions, as the expansion functions fk of x, such that fk of x is equal to 1 plus rk divided by c. And I've added that coefficient c there arbitrarily just to make this non-dimensional, because when I explained this last week it was just 1 plus r. But then r has units of length and 1 is a non-dimensional parameter. So just to make this non-dimensional, I divide by some shape parameter c, which we can arbitrarily decide what it is. So shape parameter. We'll talk about that further when we look into matchless methods. And then if we want to find what u is, here, okay, so such that f of k is equal to the Laplace of u, which is equal to 1 over r ddr r du dr k plus 1 over r squared, the second derivative of u, d theta squared, but this is 0 because this function only depends on r. Therefore, u turns out to be rk squared divided by 36 times 9 plus 4 rk divided by c. And p k of x, which is equal to the uk dn. So it would be the derivative of that with respect to x times nx, and the derivative of that with respect to y times ny. That would be one half plus 1/3. That would have been easier to say just 1/6. Anyway, rk over c times x minus xk divided by times nx plus y minus yk times ny. Make sure this is the case. Over r. Yes. That's it. So you will see this as one function. Actually, you see it as two different functions, one with the x and one with the y. You see this is another function. You see this is another function. There are three new functions on the code. that we'll use to calculate the alphas and calculate the vector B. And we just simply add that vector B to the system of equations, and that should be able to handle the generation terms. All right. So let me move here to the PC. Open, but I've created, yeah, it's open right now. So I've created a new code here on the lectures to lecture 17 code, and executable I called dual reciprocity BEM for heat conduction in 2D. Instead of before, we just had BEM, heat conduction, and 2D. So the solution file is lecture 17, Visual Fortran project, and I've opened it up already. Let me, it's a bit longer here. Okay, enough space here. So let me show you the structure of the main code is pretty much identical. The only thing that I've added to the common variables is this block that has the generation terms, okay? So the way I've arbitrarily say that the form of the generation is going to be, the user can impose 3 coefficients for the generation. A constant, an x coefficient, and a y coefficient, okay? So I'm allowing the generation to be a linear function, x and y. That's it. You can change it to whatever you want. You can make it parabolic. You can make it exponential. But just for the purpose of exposing this and showing how it works, I've added this common block, and in the input file you will see, in the input routine you will see that there is a line that requires the user to put this in the input file. Okay, a constant coefficient, an x coefficient, and a y coefficient. That's it. And I've added another common block here at the end that basically contains 3 things. C is that shape parameter of the radial basis function, which is basically a measure of the distance so that we can non-dimensionalize the radial basis function. This is the coefficient alphas, and this is a vector B. Notice that the coefficient alpha is of the size of the total number of points, and then max is our total number of points. That includes boundary and internal points. While the vector B is only MB max. It's a number of boundary points only. All right? And the structure of the code remains the same. Call the input file. With the input file, let's go to the input file to show you the only thing that I changed here is basically when you open the same file. And by the way, I didn't change the name of the file. We should call the file dual reciprocity BEM AC2D instead of just BEM. So I'm going to change the name of the input file and the name of the output file as well. Okay? So we changed the input file. The input files DR. Make sure I didn't go over the line 72. So I asked for a title. I asked for a thermal conductivity, and then I also asked for 3 parameters for the generation. UC, UX, UY. And then the rest is the same. The number of segments, number of points per segment, where the segment goes, what's the midpoint of the segment, what's the final point of the segment, and then the boundary conditions for each segment, and that's it. And then it goes back to the, I'm going to save this and compile it. All right, so let me go back to main. After that, it goes to the preprocessor. And I didn't change anything in the preprocessor. It's exactly the same. The preprocessor, remember, it takes that input information and builds the boundary element discretization. From segments, it builds the boundary element discretization depending on what the user establishes the boundary element sizes to be, or the resolution to be. And it creates also the boundary condition for each of the boundary elements. And that's it. That's the only thing it does. Now, one thing I do extra here is the scaling factor, or shape factor C, which I make equal to the square root of the square of the average distancing in X plus the square of the average distancing in Y, which I had already calculated in the preprocessor. In the preprocessor, I had calculated the average distancing in X and in Y in the boundary element resolution to distribute the internal points. So I used the same thing to calculate C. It's just that average distancing. And basically that's used as a non-dimensionalizing parameter in the RBF. The RBF being now 1 plus R divided by C. That makes the RBF completely non-dimensional. Okay? And one thing that I took away from here, from the preprocessors, I don't know if you remember, at the end of the preprocessor file there was a loop that took all the took the boundary points for post-processing purposes, for output purposes. It took the boundary points from the center of the element to the corners, so that the tech file can actually show the full geometry, including the corners. Okay? The boundary elements that we use have the node right in the center of the elements, and that's still calculated that way. For these purposes, okay? XS and XY, remember, has the 3 nodes, 3 values of X and 3 values of Y, the 3 nodes of each element. I'm sorry, that's the segment. X and B max has the 3 nodes for each element, while XC has a location of all the boundary and internal nodes. And that it's at the edge of each other. So I removed this from here because I need those nodes to still be at the center of the element for the purpose of using them for the dual reciprocity process. All right. So then I perform collocation, and I didn't change this file at all. Collocation is basically the routine where the matrix G and the matrix H are calculated. Nothing changes because those remain the same. So I loop over all the boundary elements, and I loop over all the boundary elements. So I loop over all the boundary elements to collocate, and I loop over all the boundary elements to integrate. So I put the source point at an element and integrate over all the elements. I put the source point at the next element and integrate over all the elements, and that's how I generate the matrix J and the matrix H. So at the end of this process, H and G are generated. And then I calculate the diagonals of H through equipotential. That remains exactly the same. This is a new routine here called dual reciprocity. And that routine, what it does is basically calculates the vector B. That's all it does, okay? It expands the generation term, the generation function U, which is now a linear function of X and Y. It's UC plus UX plus UY. And it expands it in terms of radial basis functions. It calculates the coefficient, expansion coefficients alpha by inverting, or basically solving the system of equations. And then it uses that alpha in combination with U and P and G and H to produce a vector B. Okay, there's a lot of algebra. I don't expect you to digest this subroutine now, but you can go back and confirm that it matches exactly what we wrote on the notes. All right? So basically the subroutine dual reciprocity first builds a collocation matrix and generation vector. The collocation matrix F are the RBF functions F, okay, collocated at all the points, all the XC points. That includes all the boundary and internal points. Okay? For all the functions, all the RBF functions XK and YK. Okay? Or the shape parameter C. So there's a function called FRBF. And the function FRBF, if I look at the RBF routine, there's a function called FRBF that uses a given value of X and Y and a given collocation point XK, YK and a given shape parameter. And it's just simply 1 plus R over C, where R is the square root of X minus XK squared plus Y minus YK squared. That's all. So that's the RBF function that we're using.
And also remember, u, which is the Laplace of u is equal to f, is equal to r squared divided by 36, 9 plus 4 r over c. This is the same thing that we just wrote in our notes. And the normal derivative of u, well, u has an x derivative that looks like this, and a y derivative that looks like this. This is 1/2 and 1/3 and so on and so on. The same thing that we just wrote in our notes. So we're going to be calling these four functions from these routine dual reciprocity. All right, after I form the vector f and the right-hand side vector b, which I call alpha, okay, but it's the right-hand side vector b, which is basically the generation term. The generation term is uc, is a constant value, plus the coefficient ux times the location x, coefficient uy times the location y, divided by tck, divided by the thermal conductivity. That's what the right-hand side function b is. So now I have a matrix and a vector. What do? I decompose the matrix, and you decompose the matrix. By the way, I also slightly modify this LU decomposition routine to not only include the size of the system, but the dimension of the system. Because we're going to use this LU decomposition now twice. Notice that the matrix F is the size of all the points, boundary and internal points. But when we decompose the system of equations G and H, that's only the size of the boundary. Okay, so we're going to use this routine twice with two different sizes. In this case, all the points. And then what we do is do a Hilbert substitution, basically the right-hand side vector and the matrix F, and solve the system. So now after these, this vector AL contains the alphas. That's the alphas of the expansion of any function, in this case our function B, which is a linear function, into radial basis functions, alpha times F's. Now I compute the dual reciprocity vector and put that into BDR. I'm going to call that B dual reciprocity, so that this loop here, which is a few lines, basically has G times P, H times U. That's it. That's what B is. Remember that G is the influence coefficient matrix Gij, and H is the influence coefficient matrix Hij. Okay, we already calculated that on the previous routine. All we need to do is multiply that times P and multiply that times U for every point, collocating on the boundary and on the interior. So basically, collocated all the points, boundary and interior, integrating over all the points, and basically that's the vector B. And the vector B is a multiplication of these matrices. I use F because I don't want to declare another matrix for that. So I reuse that matrix F, which I don't need anymore. I already calculated the alpha, so I don't need the matrix F anymore. So I use this matrix F, which I fill with G times P minus H times U, multiply times the alpha, and that's the vector B. That's exactly the same what we wrote in class, what we wrote in the notes. So now I have the vector B. Go back to the main code, go to the solution. Now the solution before consisted on simply shifting some of the rows of the matrix H and the matrix G, depending on what type of boundary conditions we had, right? That's all it consisted, so that as to form a system of equations AX equal B. Now, we're going to do the same, but now we have H times T is equal to G times Q plus a vector B. We have an additional vector B, the vector of dual reciprocity. So we need to account for that one. And that's it. So I changed this a little bit before. I decompose the matrix G. I'm gonna decompose the matrix H. There's nothing changes. Basically, if the boundary condition type is 1, I switch the rows of H and G, negative of the rows of H and G. If boundary condition is type 2, I do nothing. If boundary condition is type 3, I still do stuff. I didn't want to change this, but you know what to do now. That's part of your project. And then I LU decompose H. In the other code I gave you, I LU decompose G. So I'm using matrix H instead of matrix G. Is essentially the same thing. I divide the boundary, if the boundary condition is type 2, which means flux, I divide that by TCK, by the conductivity, and multiply times -1. because the boundary condition should be the normal derivative, not the flux. Then I multiply the boundary conditions vector times the modified matrix G, which contains now rows of H and rows of G, depending on what kind of boundary conditions. And this will contain either temperatures or fluxes, depending on what is given. And then at the end, I add the dual reciprocity component to each of the entries of this vector. Okay? So that's the only change. This is basically the only change, this line, to this routine. Once that's done, now I call the LU back substitution with this right-hand side vector B, and the right-hand side vector B will now contain the solution. So if boundary condition is type 1, the temperature is the boundary condition, the flux is the solution vector B. If that boundary condition is type 2, temperature is the vector B, solution vector B, Q is the boundary condition. The boundary condition type 3, you did this for your problem. Okay, so I remove from this routine the calculation of internal temperatures and fluxes. Okay, and I moved them over to a new routine. So I didn't want to do it, I didn't want to clog this routine with that, because now not only we need to calculate the internal temperatures and fluxes, we need to add the dual reciprocity contribution to that. So that's slightly more involved. So basically, I put that into, after the solution, there's a subroutine called post-processor. That calculates internal solution field. So if you go to the subroutine called post-processor, that was basically the last part of your solution routine before. And essentially, do the same that we did before. Now notice that the first part of this routine is where I shift the boundary points and normals to the element end nodes, because I want to calculate temperatures and fluxes at the edge of the elements, not at the center of the elements, for output purposes. I want TechPlot to be able to print those contours all the way to the corners. So I shift everything to the edge of the elements instead of the center. This was before in the preprocessor routine. Okay? And then I compute the boundary end nodes and internal temperatures and fluxes the same way I did it before. If it's on the boundary, what I do, I slightly shift the location of the boundary point, because these integrals are hypersingular. So what I do is I slightly shift it into the interior by a 20th of the length of the element. Okay, so I cheat a little bit, but that's absolutely necessary. Okay, so see what I'm doing is I need to calculate the temperature at these new locations on the boundary. Okay, if it's on the boundary, the integration routine is not going to be able to handle a collocation point right at the edge of an element, because those integrals are hypersingular. So what I do is I shift it inwards using the normal vector and the length of the element by a factor of 20. I shift that point inwards into the domain by a little bit. Okay, so that's something imperceptible. And then I calculate the temperature, the fluxes at each of these points, whether they're in the interior or on the boundary, all the points. All right, now the only thing that changes on this loop is this generation contribution. The generation term contributes to the calculation of internal temperature and fluxes with this term Bi, this term Bix, and this term Biy. To the temperature with these, to the gradient in X with these, and to the gradient in Y with these. So basically I'm calculating the terms that I wrote in the notes. And again, I don't expect you to decipher these, but I'm basically doing the same. I'm basically doing G times P, H times U. Okay? So that's how it's done. And then this new term Bi, Bix, and Biy is, that's akin to the vector B, but when you do it on a point-by-point basis, it's not a vector, it's just a value, it's a scalar. So basically, you add Bi to Tc in the variable. So this is the contribution to the internal temperature due to generation. This is a contribution to internal flux due to generation. All right? So then I multiply these values of fluxes by the negative of the thermal conductivity to make them actual heat fluxes instead of normal derivatives, and do the same in the interior. All right? And that's it. And then the output is exactly the same. Nothing changes in the output. We don't need to worry about whether there was generation or not. The output is going to take the solution output to a file. And by the way, let's change this so that the output is made to a file called dr.bm, and the triangulation is also sent to a file called dr.bm, TechPlot file. Okay, so let me compile this. Let me build the solution. By the way, I use shortcuts, but you can always go to build. If you want to compile a single file, you just click compile. I use Ctrl F7 for that. If you want to build a solution, it's Ctrl Shift B, or you just click here.
What's the difference between the two? The difference between compiling and building a solution?
But when you're compiling, you're just basically turning this file, not all the files, this file, into an object code. Okay, that's a pre-assembled code. It's not executable. Now, when you build, you take all of the object codes corresponding to each of these Fortran files and link them together into a single executable. That's what the build means. Okay, and when you build, the studio determines which one of the object files are outdated. So if you haven't compiled one of them, it will compile it for you and then link them together. Okay? And that's common, that's the same regardless of the programming language. Okay? If you do it in C++, it's exactly the same. You compile and link. That's a two-step process to produce an executable. All right, and now we need to, let's go to the data folder. So I'm going to change the name of this file to dr so that it recognizes it. I'm going to delete this output file. I'm going to delete the template file because I'm going to produce a new one. And the layout file I'm also going to call dr.bm, but I'm going to open the layout file because the layout file is associated with a template file that's called bm. I'm going to associate it with a template file called drbm. Save this. All right, so let's look at this input file. I'm going to solve a heat conduction problem in a square with a thermal conductivity of 1 and a generation of 1,000, 0, 0. Okay, that means that it's a constant generation. Okay, the linear terms and x and y have no effect. So we have a constant generation throughout the domain of 1,000. That's 1,000 watts per meter cube. All right. This we're going to use a discretization of 20 elements, and each of the 4 segments of the square goes from 0, 0 to 1, 1. Okay. So it's 1 meter by 1 meter square with a material that is 1. That's a very insulating material, and all the boundary conditions are type 1, 0. So we have temperature equals 0 everywhere. Okay. If I didn't have a generation, what would be the solution of this problem?
Same as this previous one that we had?
No, notice it's 0, 0. And the previous one we had 100 on the,
Because we had the driving temperature.
yeah, we had a driving temperature on the boundary. In this case, all boundary conditions are homogeneous. Okay, first kind homogeneous. So if all the boundary temperatures are 0, the solution in the interior has to be 0. Okay, but now we have a non-homogeneous governing equation. We have generation, and what should this do? We should see a bump in the temperature coming through the center, and it should be perfectly symmetric, right? Because it's constant. So that's what I wanted to do. I wanted to make sure that we get a symmetric distribution, so that's a way to validate the code. Okay, so we should see a bubble of temperature coming out of the center, and keep the 0. We should stay on the boundary. Okay, so let's this is okay. So I'm going to go here, which is already compiled, and I'm sorry, not here. Here, compiled and linked. And go back to mine. It doesn't matter where I am. And I'm going to use, these were questions that people were having about how to execute the code. If you go to debug and click start, or just simply click start here, what that does is start debugging. It will basically execute the code on a controlled manner. Line by line, it will give you access to the assembly code so that you can actually detect and actually read the value of the variables and so on. It will actually help you debug the code, but that's not how you want to execute a code. Okay? If you really want to execute a code, I probably did it too fast when I was doing this in class. You go to this debug and start without debugging. Okay? So I would just simply execute the code. Or you can just go here and click on this executable, double click on the executable, which was created 5 minutes ago when we built the solution, okay? So you go here, and I use Ctrl F5, which is a shortcut for start without debug. All right, so it executed very fast, no errors, no problems. Press any key to continue. So if we go back to the folder, data folder, we should see now the output file. Let's look at that output file, make sure there are no weird things. Okay, the boundary results, remember this is all x, y, and xy on the boundary. These are all the temperatures. And as expected, all the temperatures are 0. Okay, now look at all the fluxes. And one thing that we should expect is the fluxes to be perfectly symmetric. If we go from boundary element 1 through 20, which is the bottom edge, right? We should see the flux small and growing through the center. So we should see the flux 45, 147, it's growing, it's peaking right at the center, element number 9 and 10. And then, 10 and 11. And then going back, and it's perfectly symmetric. This number is equal to this one, this number is equal to this one, this number is equal to this one. Positive is correct. Why? Because if you have positive generation of energy, that energy needs to be dumped somewhere. Okay? The energy needs to be dumped somewhere, it needs to go away through the boundary. That's the only place where it can go through, it can escape. And leaving, in this case cooling, means positive. Cooling is also always positive, heating is always negative. Okay? Okay, the direction of the flow, remember the flux is always the negative sign on the heat flux is minus k dTdn. The negative is an artifice. We put it there so that we ensure that the flux always goes in the direction from higher potential to lower potential, from higher temperature to lower temperature. If you don't have that negative, remember the gradient is always going to go in the direction, ascending direction, from low to high. But because physically the flux is defined as the vector that goes from high potential to low potential, high temperature to low temperature, we put the minus sign. And the scaling factor is the thermal conductivity. Okay? So it is positive means cooling, that's correct. Now the next 10 elements should be perfectly symmetric the next 20 elements should be perfectly symmetric. So whatever escapes through here needs to escape through here. And look at this number, 4569 is identical, 147. So that's a good indication that things are correct. Let's look at the interior results. Make sure that nothing is weird there. All the temperatures are positive as expected. We have a positive generation. That means all the temperatures need to be positive. All the temperatures are positive. Remember these are not fluxes. These are not normal fluxes. These are gradients, okay, or negatives of gradients in the x and in the y direction. So some of them are going to flip signs depending on where the arrow is pointing. Okay? Now the best way to visualize this obviously is through a contour or surface plot. So I'm going to open the layout file, which should now point to the Steckler file. And there it is. So it produces temperatures. I use a generation of 1,000 because I know that at 1,000 this would produce temperature around here, 76 right at the center. As expected, it's perfectly symmetric at the center. These are contour circles, you can see. And the temperature on the boundary is kept at 0. See, the flux is perfectly coming at 45 degrees. And all the energy is leaving through the boundary, as can be seen. All right? So this is a good test. That doesn't mean that it's correct. I know that it's correct because I know the analytical solution to this problem, and I know that the temperature at the center should be around that, 70-something. Okay? But at least it's a good test. You can verify that your code, there's nothing weird with the code, because the solution is perfectly symmetric. What you impose is perfectly symmetric. If I were to change, let's say, if I go to the input file and were to change, say, this coefficient here and make it 500, now we have a generation that depends on x, right? So we have 1,000 plus 500 times x. So we're going to have 1,500 here, okay? And 1,000 here, so it's changing. So since it's changing, since it's growing, increasing in that direction, we should see that bubble actually shift to the right. Okay? Most of the temperature, the highest temperature in the field is going to be generated on the right. So if I execute the code, and then I open the layout, see what happens. It shifts a little bit to the right. Maybe not enough, but you can see that these things are now larger. These ones cannot be seen because I guess it's cut right here, but this is definitely shifted to the right. I can make it larger, and you can see that bubble shift to the right. And the temperature is higher too, because now the higher generation is 1500 instead of 1000. Okay? I can make this number 5000, and that would really push it to the right. Right? Now it's the generation is 5000. It's out of the scope here of this legend, so I need to change the contours, but it's definitely pushed to the right. Okay, I can see that the maximum is right here. All right, and you can keep playing with these and finding. I can make this 500, and I can make this 500, and this will also be not symmetric, but symmetric with respect to the diagonal. And this fast, you get a new solution to the system. So now it's symmetric with respect to the diagonal. It's been pushed a little bit off, and it's not clear, but this distance right here is longer than this distance right here. All right? And the temperature now larger than before. Okay, but if you try to do this solution by hand, it's a square, homogeneous boundary conditions, in a linear generation term, you need to do superposition, separation of variables, and so on, and it will take you a while, and it will be in terms of infinite series, and you will not get this resolution. Okay, any questions? All right, so I'll post these and on the Canvas side as usual, and you have liberty to play with it. We're not going to do anything with it in terms of a project or anything like that, but you can have it at your disposal. All right? So if there are no questions, I'll see you on Thursday. Again, I'm not going to be here, so the day you have to turn in your project. So I'll hope to see that.
See?